let's just apply it. Okay, let's just solve a problem that you have already seen, okay, in class. Okay, so you must have seen this in the video, I guess. U1 x1 y1 equals x1 plus 2 root y1, and u2 x2 y2 is equal to x2 plus 2 root y2. All of you have seen the video of this one? Yes. And the endowment is 4004. Have you all seen this? I've asked, I have done that in the video, like how to find the efficient allocations for this one. Okay, so if you see, if you recall, you get these as set of efficient allocations. Is that okay? Do you agree we'll get all these allocations as Pareto efficient? Yes or no? When these are the utility functions, let us try and get that using using basically weighted sum of utilities. We'll try and maximize weighted sum of utilities, and we'll try and get all these, if possible. Okay, let us see what all we can get. Okay, so let's write this problem, which is maximize with respect to x1 y1 x2 y2 alpha x1 plus 2 root y1 plus 1 minus alpha x2 plus 2 root y2. Okay, right? Okay, subject to the constraint that x1 plus x2 is equal to 4, y1 plus y2 is equal to 4. Okay. Is that fine? Do you agree this is how we can write the optimization problem? And of course, there are also non-negativity constraints. So you can write it like this. Okay. So this is the problem that we would like to solve, and we would like to see how, as alpha changes, how the solution varies with alpha. We'll also see that. So we'll find solutions to this particular problem for every possible value of alpha between 0 and 1. So let's look at this problem. Okay, so if you see, you can even split this problem. I mean, it's because it's kind of additive. So it's very easy to split this problem, and you can just write it like this: maximize with respect to x1 x2 alpha x1 plus 1 minus alpha x2 plus maximize, and this is subject to x1 plus x2 equal to 4. Okay, and this is maximized with respect to y1 y2 2 alpha y root y1 plus 2 alpha, sorry, 2 1 minus alpha root y2. Okay, subject to y1 plus y2 equal to 4. Yes, we can split it like this, right? Because if you see, this part of the problem is not really affected by y1 y2, and this is the only constraint that matters. So if you just solve this separately and solve this separately and add the solution, and add the objectives, then it's going to give you the same solution as solving this entire problem together, right? I mean, it's not going to make any difference. Yes or no? Okay. Now, so let us start with alpha equal to half. What is x1, y1, x2, y2? It belongs to a set. Okay, so let's write the entire set for alpha equal to half. Notice that for alpha equal to half, this is like half x1 plus half x2. If you maximize half x1 plus half x2 subject to x1 plus x2 equal to 4, you'll get set of all x1 x2 on this x1 plus x2 equal to 4 line, right? Yes or no? So basically any pair will solve this problem. Yes or no? Is that okay? So basically what you're going to get is, so this belongs to the set. Okay. And what about when alpha is half? This is root y1 plus root y2. When you solve this problem, what are you going to get? Maximize root y1 plus root y2 subject to y1 plus y2 equal to 4. Anybody? Y1 equal to y2 equal to half. Y1 equal to y2 equal to 2, right? Yeah. Is that okay? So when alpha is equal to half, then any this can be anything, theta, where theta belongs to 0, 1. Okay, x1 is 4 theta, x2 is 4 times 1 minus theta, y1 is 2, y2 is 2. So basically, all these points you're going to get, because all these points are where x1 and x2 can take any value between 0 and 1, 0 and 4. X1 and x2 can take any value from 0 and 4. Okay, and y1 and y2 are 2 each. Okay, so basically you're going to get all these solutions, for theta, for alpha equal to half. Is that clear? Okay, now let us consider for alpha less than half. For alpha less than half, what would be the solution to this maximization problem? Anybody? When alpha is less than half, 1 minus alpha is greater than half, right? So which one will you choose? 0, 4. That's right. So x1 will be 0, x2 will be 4. Okay, and what about y1, y2? Just solve this problem. So this is a, if you use the indifference curve approach, it's a 2 variable optimization problem. You can easily do it. Put y1 on the horizontal axis, y2 on the vertical axis, and if you plot the level curves, they'll look like this. So you just have to use the tangency condition to get the solution, right? So what is the slope of the indifference curve in y1, y2 space when the objective is this? That is what you need to find. So let's just do that. So let's first find the partial derivative of this with respect to y1. What are we going to get? Alpha by root y1, right? Okay. And what is the partial derivative of this with respect to y2? 1 minus alpha by root y2. And what is the slope of the constraint? 1 in absolute terms. So the solution must satisfy this, right? Yes or no? Okay, so what are we going to get? So if you see, you're going to get, just take this to the numerator, you're going to get alpha root y2 upon 1 minus alpha root y1. is equal to 1, which is going to give you what? Y2 by Y1 is equal to 1 minus alpha by alpha squared. Yes or no? Okay. Now notice that alpha is less than half. So 1 minus alpha is greater than half. So 1 minus alpha upon alpha is greater than 1. So y2 by y1 is greater than 1. That means y2 is greater than y1. That means we are looking at these points. And as we change alpha, we'll keep getting different points. I mean, so depending on the alpha, you'll get a point here. I mean, if you keep reducing alpha, you'll keep getting a point closer to the origin of 1. Is that clear? Because y2 is greater than y1, right? Y2 is greater than y1 means what? Y2 is greater than y1 means that uh, so total amount of y1 plus y2 must be 4. So y2 is greater than y1 implies that y2 is greater than 2, which means y1 is less than 2. So which means we are talking about these points, right? And as you change alpha, you keep getting different points over here. Similarly, if you solve for alpha, this particular problem for alpha greater than half, you'll keep getting different points over here. Is that clear? Okay, and notice that it's a very nice trick. I mean, just with with this very simple problem, by maximizing the weighted sum of utilities, you can actually, I mean, you are able to get most of them. Okay, and if you want to show an allocation is not Pareto efficient, just show that there exists a superior allocation than that. Okay, so I'm not writing these two now. You can just write that yourself. But this is how you can actually solve this problem. Okay. So of course, I mean, if you want to also mention, write this over here, then you just need to solve this, because this is two equations in two unknowns. Okay, so this is y2 equals 1 minus alpha upon alpha square y1, and then you also know that y1 plus y2 is 4. So two equations, two unknowns, and you can solve for y1 and y2. Okay, and then you can fill these up. That's how you can fill these up. And similarly over here. Is that clear? And then of course, as you change alpha, you'll get different values here, different solutions here. And clearly, as alpha approaches 0, you will approach this point. As alpha approaches 1, you'll approach that point, the origin of individual 2. Is that okay? So you'll get all these solutions for different alphas. And for alpha equal to half, you'll get the entire line like this. For each different alpha less than half, you'll get exactly one solution here. For each of the alphas, you'll get precisely one solution each for each alpha, for less than half, in here. So like for example, for alpha equal to 1 by 4, solution might be somewhere here. For alpha equal to 1/3, solution might be somewhere here. For alpha equal to 1 by 5, solution might be somewhere here, and so on and so forth. Okay, and for alpha greater than half, let's say for alpha equal to 3 by 4, solution might be somewhere here, and so on and so forth. Is that clear? Okay. This is a very nice approach, to solve for Pareto efficient allocations. Okay,